Hello everybody, welcome to my class on point of inflection and extrema in calculus. Extrema means we'll deal with maxima and minima in calculus. So today is Buddha Purnima, so happy Buddha Jayanti to you all. May the Lord Buddha enlighten us on the path of truth, love, peace and prosperity. Buddham Saranam Gacchami. Dhamma Saranam Gacchami. Sangham Saranam Gacchami. So, before I go further into the class lesson, I would first like to pay my gratitude to all the students in my classes for celebrating my birthday. So here, I'm going to produce the video you made for me. So thank you all for this wonderful video. Let's watch it first and then we go further into our class lesson for today. Welcome to my class. Okay guys, before we go through the maximum and minimum point and the point of inflection, we first see that what is called increasing function and what is called the decreasing part of the function. So for example, if you are given a graph like this, any function, and then for example, a part of graph is like this. So if you draw the tangent at this point, you can see that this tangent makes acute angle with the x-axis. That means gradient at this point dy by dx is positive, that is greater than 0. And at the same time, you can see that as you move along this way, I think up to here at least, all right, then you will see that as you are moving through this path in the curve, you can see that you are going towards right, that means x is increasing, and also at the same time you are rising up towards y-axis, that means there is increase in x for increase in y, or for increase of y for increase in x. That means the change is in the same order. Therefore, from here to here, you can say that this is the increasing part of the curve. So from this domain to this, the curve is increasing, and at this point it is found that dy by dx is greater than 0. So therefore, condition for function to be increasing is that dy by dx is greater than 0. Now, if you consider a tangent at this point, for example, and if you extend this to the x-axis, and if you measure this angle, this is obtuse angle. So in that case, you can see that the gradient at this point is less than 0. That means at this point, the gradient makes obtuse angle with the x-axis, therefore dy dx is less than 0. But what happens in this part? You can see that in this part of the curve, up till here at least, you can see that as you are going right, that means x is increasing, y is descending down, that means y is decreasing. And if you move from this point to the left, then x is decreasing this way, but y is increasing. So here the change is in inverse direction. Change in y and x is in inverse direction to each other. And therefore, in this case, we can say that this is the decreasing part of the function. And at any point, if you draw tangent along this decreasing part, you'll see that the gradient at that point is that point gradient angle, it makes obtuse angle with x-axis. Therefore, gradient at that point is negative. That is, dy by dx is less than 0 is the condition for the decreasing part of this part of the function. Now we summarize the situation over here. You can see that this is a curve. It is also called the concave down shape or concave. And this you can see, this is called concave up or convex curve. So these three lines are taken as example for the tangent at different point. So you can see that from here to this maximum point, the gradient is always positive. So this is the increasing part of the curve. At this point, the gradient is 0 because it will be parallel to x-axis. Therefore, this will be called the stationary point. And then after you descend from here, this is the decreasing part of the function. And at this point, you can see that from x-axis, it makes obtuse angle. So gradient at this point is negative. Therefore, this is the decreasing part of the function. Similarly, in this concave up curve, you can see that this gradient is negative and this is the stationary point. Obviously, in this case, this is the minimum point. And then another side, it is positive gradient. That means this is the increasing part of the function. And same thing have been described over here. And this sort of thing we can illustrate with one example here. So in this example, it states that given the function fx equals to x cube minus 3x, find the range of values of x for which fx is increasing and it is decreasing. So first of all, what we can do actually, we have to draw the graph for this function. So here it is, the graph has been drawn for you already here. So in order to draw the graph, we require points on x-axis as well as in y-axis. So what I have done here, that I put y equals to 0, then I have these many coordinate values for x, and when I put these values to this function, I have the y coordinates also. So these are the points that I have accumulated here. And also you can see that if x is 0, then y is again 0. So 0, 0 is another point. Next, I have taken first order derivative and that equal to 0 because at the stationary point, you can see that first order derivative is 0. So from here, we have 2 points, x equals to plus and minus 1. And by taking reference of all these points, we can draw a graph like this that we have done in functions and graph. So from this graph, you can see that there are 0, 0, and then 3, 0, then negative 3, 0, and then we have negative 1, 2 over here, and then 1 minus 2 over here. So taking the reference of all the point, you don't need to think more than this point at this point, because this is the maximum point and this is the minimum point. The graph will definitely go over through here. And as this is 0y and this is also 0y, when x is 3 and negative 3, and 0, 0, so graph will definitely pass through this way. Then your graph looks like this. And now, just earlier we discussed that if dy by dx is greater than 0, that means it indicates that where up to the extent of the domain of x, where dy dx is 0, that means this is the increasing part of the function y equals to fx. And if this is less than 0, that means it indicates that this is the decreasing function in that domain. And when dy by dx equals to 0, that means this is the stationary point. So if you, that means this is the stationary point where dy dx or first order derivative is 0, because tangent at this point makes angle 0 degree with x-axis. So theta is 0. So tan 0 is 0. Therefore, the gradient that dy dx is tan theta in fact. So dy dx at this point is 0, and similar thing happens here also. Maximum and minimum points, these are called local maximum. And this is called local minimum or minima. And what do you call this? If your curve stops here and this is the highest of all, so you can call this point as absolute maxima. And here you can call this as absolute minima. So this is the difference between local extremas and absolute extremas. All right. But while we talk about to maximize the function about the maximum and minimum point in general, unless otherwise stated, we understand this is either local maxima or local minima. So we are concerned to find in which domain the function is increasing and in which domain the function is decreasing. So from the same graph I have taken here. So at this point, dy dx is positive, here 0 at extreme point, and this is negative over here. As at this point, dy by dx is greater than 0. So below, so this is -1. So below -1, you can see that the curve is increasing. And then between -1 to +1, you can see that at this point, dy dx is less than 0. That means from here to here, it indicates that the curve is decreasing. That means from x less than 1 and greater than -1, you can see that this part of function is decreasing part of this given curve. And again, if you go beyond 1, that is if x is bigger than 1, you can see that at this point the gradient is positive, here 0 and here also positive. That means for the domain x bigger than 1, the curve is again increases like this. And similar work you can do for the decreasing part of this curve or for this function. So condition is that dy by dx is less than 0, then x squared minus 1 is less than 0. For you can see that this is the graph of dy by dx equals to 3x squared minus 3, and you can see that this is the part where the first order derivative, that is dy dx, is negative, and this is happening in between the value of x between -1 to +1. In this way, we can say that in the domain where x is bigger than 1 or less than -1, the curve is increasing, and between -1 to +1, the curve is. So the points of inflections we are now talking of. So first of all, let's see that if you consider a water bottle like this, and without, you can see that this is one part of the curve, the water bottle, and this is the another part of the curve. You can see that from concave down, change from concave down to concave up over here without attending any maximum or minimum point, that is local maximum or local minimum point over here. So at this point somewhere, it has changed the concavity at some point. So this point of change of concavity is called actually point of inflection. All right, this is called the point of inflection. So here along the other side also, if you like to see actually, so you can say that concave to one side, and about this point, I think, yes, about this point, there is change of concavity when you are going down from this point over here. So in that case, you can also see that the concavity has been changed. So this point is called the point of inflection. Okay, so here you can see the definition of the point of inflections. So the points of inflections represent the points where the concavity changes, such as a transition from minimum turning point to a maximum turning point for both local or absolute extrema. So here in general, here in this in the example of here in this example and also in this example, we didn't see that there is local maximum or minima, although, but this applies. You can see later that we can find a point of inflection where there is both local or absolute extrema exist. Now let's go into the mathematical interpretation of this point of inflection. So let's see at this point, this is a kind of curve on a given axis. So here the graph, you can see the gradient is positive, and then this is parallel to the x-axis. That means gradient is stationary here, although this is not local maximum or minimum. And here in this case, the gradient is again positive now. All right. So here you saw that gradient starts from positive, then through 0 to positive again. Here you can see that the gradient starts from negative. You can take from either from here or to the down, doesn't matter. And then at this point, while changing this concavity, gradient is 0, now again negative. So change in dy dx is from positive to positive, and here negative to negative in the same direction. Then you can be definite that there is a point of inflection between these two activities. So here there is point of inflection, and here also there is a point of inflection. And at the point of inflection, your first order derivative is 0, and hence if you find the second order derivative, that means dy dx of dy by dx, all right, and then it is d0 by dx is again 0, and this sort of thing you can write d and d. This is d2y by dx square. This is not an algebra. This is a kind of denoting the second order derivative, and second order derivative is also 0 when there is a point of inflection. So we can see at a stationary point of inflection dy dx equal to 0, and the gradient dy by dx changes from positive to 0. You can see here from positive to 0, and then to positive again, and then to positive again. Then there is a point of inflection over here. And another thing you will get that from negative to 0, so from negative to 0, and then to negative again. So in this case, there is a point of inflection at this point. We shall now talk about stationary points of inflection. So you can see the point of inflections in two ways. One as stationary points of inflection, and another as non-stationary point of inflections. So we'll discuss about non-stationary point of inflection later in this class. So let's see this example. This states that find the point of inflection for this curve y equal to x cube minus 3x. So I have taken the same curve, or you can draw by using sketch the curve by using your skill that we have developed till now. So we have this curve, and we are intended to find the point of inflection. Not only the point of inflection, we'll check that whether or not this point of inflection is stationary. So from this graph, it is also obvious that the curve is changing course. That means changing the concavity from this point. We can see here. All right. So this is going to be the point of inflection, but we'll check that whether or not this point of inflection is stationary. So first of all, as usual, you find the first order derivative. So here the first order derivative is like this, that we have done this just earlier also, and we get second order derivative, that is 6x. And you know that at the point of inflection, both first order derivative as well as the second order derivative both are 0 there. So when second order derivative is 0, then we suppose at x equal to 0, that is at the coordinate where x is 0 and y is 0, because if you put x equals to 0 in the given function, in this function, your y value will also be 0. So you can say that at x equals to 0 and also y equal to 0, there is a point of inflection. So at this point, there is a point of inflection, but you have to check that whether or not there is point of inflection. Whether or not that point of inflection is a stationary point of inflection. Stationary means something starts from positive and then reaches the extreme value, then it is again negative, if you talk gradient wise. All right. So if there is change in sign in between the two positions about this point, then we can say that there is a stationary point. So here what we can do actually, as our point of inflection is x equals to 0 at this point, then we try some value in the neighborhood of x equals to 0. So let's take one value of x as 0. So here we have taken 0.3, x equals to negative less than 0.3, or you take x equals to 0.3 and another value you can take x equals to negative 0.3. That means if this is 0, we are taking very small difference about 0. So this is negative 0.3 and this is positive 0.3. That means we are testing the change of sign in between very small distance from this value x equals to 0. And we saw that when in 6x, that is the second order derivative, when we are taking x equal to minus 0.3, our value is 6 times of minus 0.3 is negative. And then when we have taken a value of x just little bigger than x, then we found in that neighborhood the here the value is positive. That means between negative 3 to positive 3 there is sign changed. Therefore we can say that x equals to 0, that is x equal to 0 and hence y equals to 0 also, that is 0 0 is the stationary point of inflection. All right. Okay, guys, let's now talk about non-stationary point of inflection. So we shall deal with this situation by taking one example. So in this example, it says that find point of inflection of fx equals to x to the power 4 minus x. Okay, you can add. Hence, state whether or not the point is stationary. That is the stationary point of inflection. 0, you can see that the point of inflection occurs at x equals to 0 and hence y equals to 0. Now we are testing the sign for or change of sign for second order derivative in the neighborhood of x equals to 0. So we are taking, for example, you can take any other value near to x, but I'm taking here one time negative 0.1 and another time it is 0.02. We suppose these two values are very close to the value of x, which is point of inflection in this case. So when I put x equals to negative value, the sign for second order derivative, that is algebraic sign for the second order derivative, is greater than 0, that is positive. And also if I am taking the positive value, the sign is again positive. So there is no sign change, no algebraic sign change between the neighborhood of value of x equals to 0. Therefore, you can say that the point of inflection at x equal to 0 is not a stationary point of inflection. Let's do one more example where we talk about extrema, that is maxima and minima. So later in this class, you will be able to find this in a few minutes or sometimes in fraction of a minute. But at this time, I'm going to explain you detail in order to make your concept clear. So pay a proper attention that how the theory of maxima and minima have been developed. So in this example, you can see it states that find the point of inflection on the curve y equal to x cube minus 3x square plus 2, and hence find the local extrema. All right, local extrema means you find either maximum or minimum point on the concave or convex part of the curve, not the absolute maximum or minimum. So here we have this sort of function given. So we gather the points so that we'll have different coordinates value to draw the graph of this function. This is better to graph in the beginning, at least while learning the situation about this sort of thing, draw the graph. So let me tell you a few more things that what you can do here. As you have got this point, you have got, and you have got this point, another, you can see that this is the minimum in the local sense, and this is the 0 point of y on the x-axis, and this you can see that is the maximum of this. You don't need to think now much about the things. You can just meet all these points. So this is the maximum point, and this is going towards 0, and from here to minimum point, and this will pass through this y0. All right, and in this way your curve will be ready. So in order to find the point of inflection and also the maximum and minimum point, you should have this sort of information that the given function, then its first order derivative as well as its second order derivative. So first order derivative, if you equate to 0, that gives you the stationary point, that is maximum or minimum point. And then the second order derivative, if you equate that to 0, that will give you the point of inflection. So from here, when you put second order derivative as 0, the point of inflection is 1, and hence the coordinate value of y is 0. So this is the point of inflection where the coordinate is 1, 0. All right. So 1, 0 is the point of inflection on the curve. And here also you can see that in this curve that, so in this way, it is concave to the left side. And then about this point, it has changed the concavity towards right side. And hence this is the point of inflection. Now, in order to check whether this point of inflection is a stationary point of inflection, which is necessary to check. All right. So we check this point in the neighborhood of x, that means in very close value of x, about here and about here we did off, or we take by estimation. So I'm taking very near value to x equals to 1. Towards the left of 1, I'm taking this value 0.9, and towards the right, I'm taking value 1.1. When you put all these values in the expression for second order derivative, so for 0.9, the second order derivative is negative, and for 1.1, the second order derivative is positive. That means there is change of algebraic sign between the neighborhood of point x equals to 1. Therefore, we can say that the change of algebraic signs in second order derivative, that is d2y by dx square, indicates that 1, 0 is a stationary point of inflection. Although at second order derivative equals 0, we have point of inflection mathematically, but it is not possible sometimes if you see practically by the graph. So let's consider a kind of example like y equal to x to the power 4, and your graph will be like this. You can see that a lot of flattened part here on the x-axis because the power of x is 4. So if you take any value less than, for example, it is 1 and it is 2. So if you take any value less than 2, so power of any value, less than 1, and part of power of 4 for any value less than 1. That means, for example, if you write 0.2 to the power 4, it is going to be very small. number, and this is the reason that it looks like as if it is flat, but actually this is not. So in this case, we are concerned to find the point of inflection if it exists. So first order derivative is like this, and second order derivative is by taking again the derivative of this thing. So 4 3s are 12 x square. So we can definitely find the point, stationary point. So stationary point can be found by using dy by dx equals to 0. That means x equal to 0. That means the curve has a stationary point at x equals to 0. And in order to find the point of inflection, we have to have second order derivative 0 at that point. So it is 12x square. You can see here 12x square equals to 0. And if you solve from here to then x equals to 0. So this indicates mathematically that, okay, because x equal to 0 also we have found by using second derivative equals to 0. So this indicates that is 0 0, that is x equals to 0 is also the point of inflection. But from the graph you can see, it can be seen that there is no transition from concave up or concave down to vice versa. So you can see in this graph is that here, because point of inflection defines that there should be transition from one concavity to another concavity, all right, or concavity to convexity, or any sort of bend where concavity changes. But here in this graph, you can see that there is no change in concavity. So we can't say that x equal to 0 as a point of inflection. Then what can you conclude about this? So we can conclude nothing about this sort of function when we are dealing with point of inflection. Let's now talk about what happens when we deal with maxima and minima by taking the derivatives of the curve. So here you can see that this is the curve y equals to x cube minus 3x square plus 2. Okay, so by taking the method to draw this graph, you can draw the graph like this, right? That we have already seen it before. And now this is the graph for dy by dx. So if you take dy dx means definitely you are going to take the dy dx for this function. So derivative for x cube is 3x square and derivative of x square is 2x. So 2 3 is 6x and the derivative for this constant term is 0. So you don't need to write. So along the same x scale, we are drawing the graph of dy dx, that is f dash x against x, okay? And then the second order derivative you can call as f double prime or double dash. So this is the derivative of this function. So it is 3x square minus 6x. So its derivative is going to be x squared means it is 2x. So 2 3 is 6 and minus 6 times x. So derivative of x is 1. So we are left with here 6. So this is the graph of, you can consider this as a function like y equals to fx, for example. So I have indicated that as f double dashed. That means we are plotting graph of f double dashed x. That is the second order derivative function. This is d2y by dx square against x. All right. So now analyze this graph. So you can see that in this graph, and we have talked a lot about that. You can see here, this is the local maximum and this is local minimum, and also there is a point of inflection. But now we see that what happens when we are moving from one side to maximum point and to another side. And then Again, we'll do the same procedure for the minimum point. We start from gradient of one side, that means dy dx from one side to through 0 to another side here. You can see while attending this maximum point. So we talk about from this point, I think this is near about 0.6, something like this, very close to 6 or 7, something like this, and very close to -1. So here, in this case, you can see that at this point the gradient is positive. That means from 0 to below 0, the gradient is positive. So gradient means f dash x, that is dy dx. You can see that the part of this curve is towards positive y. All right, when x is less than 0. All right, okay, that means gradient is also here positive. Now at 0, what happens? You can see that at 0, this is the maximum point here, apparently. All right, so at this point, dy by dx value, that is f dash x value, is 0. So you can see that at this point, this is 0. Okay. Then in another side, the gradient is negative here. That means the gradient is negative from 0 to, I think, up to 2, but let's try up to 1 only. So 0 to 1, let's check. So dy dx curve value must be negative between 0 and 1. So here you can see that this function is negative between 0 and 1. Because at this point, the gradient makes obtuse angle with x-axis, and therefore the gradient is negative, and this graph also shows that, graph of this function also shows that this is negative part. And also from 1 to just before 2, you can see that the gradient dy dx value, if you draw the tangent over here, the gradient is just still negative just before that. So from 1 to 2 is, again, you can see that the part of the curve is in the negative y side. All right, and after x, that means greater than 0 part, if you draw tangent anywhere, that tangent value will be bigger than 0. That means f dash x or dy dx will be bigger than 0. That means this is positive. So you can see that after x equals to 2, this is 1, and then this is 2. Okay, the dy dx value, the dy dx curve is showing the positive y on this axis. Okay, then let's see what happens for the second order derivative, that is d2y by dx square. So in that case, what is happening here actually in between, if this is positive and through 0 and to negative, negative starts after 0. So after 0, you can see that below 0, second order derivative negative, and finally after 0, also the value of, in this curve, after 0 until 1, just before 1, the part of second order derivative curve, or the line you can say, is negative here. So what does it conclude? That when dy by dx, when dy by dx equals to 0, so here you can see that, and eventually the second order derivative is less than 0. You can see that from up to x equals to 0, here dy dx is 2, and after that it starts to change towards from positive through 0 to negative. Then at this point, you can see that just below 1, okay, the part of this curve is negative, and here you can see that the part of the second order function is also negative, and that indicates that the curve has attained the maximum value. All right, and the similar thing you can check at this point is that here, after x equals to 1, you can see that after x equals to 1, so here the gradient at any point up to here is negative. Then through 0, at this point, this is the minimum point, so it is 0, and about this point, this is positive. So change in dy by dx eventually is positive after, you can see that after x equals to 2, after x equals to 1. So after x equals to 1, you can see that the part of second order derivative is positive. That means it is towards the positive y. So in this case, you'll see that second order derivative is bigger than 0. That means while dy dx equals to 0 and second order derivative is bigger than 0, then the curve has minimum point. You can see here also that the curve has minimum point. And if second order derivative is less than 0, that is eventually it is the change of first order derivative is the second order derivative is less than 0. That means while in this process, the curve has attained here the maximum point. So therefore, in order to find the maxima and minima, you will have condition like this, that in both the cases, all right, in both the cases, like for maxima or minima, I'm talking about local maxima and local minima. So one point is fixed, that the first order derivative dy by dx equals to 0. And if your second order derivative is less than 0, that means it attains the maximum point, that is the local maximum point. And if your second order derivative is bigger than 0, that means it attains the minimum point. So condition for maxima or minima in general, here we talk about local maxima or minima, not the absolute maxima or minima. All right. So the first condition and the common condition for maximum and minimum is dy by dx equals to 0, or you can say f dash x, that is the first order derivative, is 0. And if the second order derivative is positive, then it indicates the minimum point on the curve y equal to fx at some value of x equals to alpha. And if the second order derivative, that is f double dash x, is negative, that means the curve this has maximum point at some value of x equals to beta. And condition for the point of inflection is that here we require dy dx equals to 0 at this bending point, somewhere like this. Okay, and also the second order derivative is 0. So by taking this condition, we can find the point of inflection. And you know that in order to check whether the point of inflection is stationary or not, we have to check in the neighborhood of x, that is the neighborhood of this point of inflection, where we have to see that whether there is algebraic sign change between two neighborhood of, or at least two neighborhood of the point of inflection. So here we have two things. One is that for maximum or minimum, that is also called the local extrema, first order derivative is bigger than 0 through 0 to less than 0. That means the curve has attained the maximum value. That means if you consider a curve like this, so it is dy dx, that is gradient is positive through 0 to negative. Then you can see that it has attained the maximum point. And if the first order derivative, that is the gradient, you can see that it is negative, that means less than 0, and it is a stationary point that is parallel to x-axis. So gradient is 0 at this point. So if the gradient is negative through 0 to positive, that means you can see that the curve has the minimum point over here. All right. But in the point of inflection, you can see that, like here, for the local extrema, you have positive through 0 to negative, or the gradient negative through 0 to positive. But here in this point of inflection, you will see that the gradient is positive through 0 to positive again, or negative through 0 to negative again. So let's see in this example that it says that maximize fx equals to x cube plus 5x square minus 7x minus 2, and also find the point of inflections, if any. Okay, so you know that you have all these three information necessary actually. So first of all, the given function, then the first order derivative. You can see that derivative of x is 3x square when you use formula x n n x n x n minus 1. Okay, and then find the derivative of the derivative again, that will give you the second order derivative. And you know, for now maxima and minima both, the first order derivative must be 0 in order to have a stationary point, either maximum or minimum. So once you put this equals to 0, and then you have the value of x as these two values of x, because this is quadratic equation. Now you can use calculator to find these values. And also you need to find the second order derivative you have here. So now put this value of x, that means one of this value of x. So here I am taking first of all 0.594 in the second order derivative, and my answer is positive here. That means it is indicating that at x equal to 0 there is minimum point. All right, and another time I have put this value minus 3.927 in the second order derivative. Here it is, and I got the negative answer here. Negative answer in negative number, which is less than 0. It indicates that the curve has the maximum point at x equals to minus 3.927. So now you have confirmed that this is the minimum point. So you get corresponding value of x. So you put this value to the function, you will have the value of y at that point. And if you put this also in the given, in the same function, you will have the maximum value of y at that point. So here it is. You can see that the maximum point is negative 3.927 and 42.036. You can usually we indicate these points up to 3 decimal places. All right, and similarly you have now the minimum point over here, where you have got this as positive. So minimum point is 0.594 and minus 4.184. And for the point of inflection, you know that the second order derivative is 0. So about this, the point of inflection we found as negative 5/3. Now in the neighborhood of this, if you check if there is algebraic sign change, that means the point of inflection at x equal to minus 5/3 is the stationary point of inflection in that given curve. So since there is change of algebraic sign in the neighborhood of x equals to minus 5/3, so therefore x equals to minus 5/3 is at a stationary point of inflection. Hope it makes sense.
So here's the summary of the work that we did today. Next page.
Another page.
Next page.
Another page.
And next page.
Another page.
Next page.
Another page.
And next page.
Another page.
So here's the end of our summary, and
Thank you for your patience.